today's lesson is solid state. The main objective of this chapter is that this chapter deals with the study of different kinds of solids. This chapter deals with the study of crystal unit cells. This chapter deals with the study of different three-dimensional pattern of arrangements like 𝗵𝗡𝗃 lattices, and also this chapter deals with the study of the three-dimensional closed packing structures, and in this chapter we have to study about the imperfections in the solids, and lastly we have to study the properties of the solids. So, overall view of this chapter is like this. For our convenience, I am going to teach this lesson in different parts. Welcome to my first part of solid state. Now, in this part, I would like to discuss first of all what are solids. We know matter exists in three states: gaseous state, liquid state, and solid state. These two states are simplest states. Solid state is in a compact manner. The solids are rigid because the constant particles are held together by strong forces of attraction. When compared to the gaseous and liquid states, solid state is having highest melting point. Solid state is having high melting point and boiling points because their regular pattern of arrangements of various constant particles in a rigid places. So, in this solid state, generally solids are of two types: crystalline solids and amorphous solids. When we talk about the crystalline solids, these crystalline solids have proper arrangements. They have proper pattern of arrangements of constant particles. Crystalline solids have sharp melting point. If you heated a crystal, then it melts at a particular sharp point, say for instance at a x degrees centigrade. The crystalline substances are non-conductors in solid state. Why? Because in solid state all the particles are strongly held by forces. So, there will be no movement of free electrons. That is why they are non-conductors in solid state, but conductors in fused or aqueous state. And when we talk about the crystalline solids, they are anisotropic. Anisotropic. That means, if you observe the pattern of arrangement of atoms or ions in the crystal, this is a repeated pattern of arrangements. Why they are anisotropic? Because if you take the physical properties of crystalline solids in this direction, physical properties like conductivity or thermal conductivity, that is one type in this direction. If you take the same property in this direction, as the atoms or spheres are less, so that the property will change in this direction. Anisotropic is that having different properties in different directions, that is called as anisotropic. Generally formed in the nature, nature trends to form crystalline solids definitely. Why? Because crystalline solids have less entropy. That is why nature tend to form crystalline solids. When we talk about amorphous substances, the term amorphous was taken from a Greek word which means no form. That means amorphous solids have improper arrangements of their constant particles, and the amorphous forms, atoms or ions are arranged irregular arrangement. Amorphous solids have no sharp melting point. Even though they are by name solids, but their properties are just like liquids, because amorphous forms are having flow just like liquid. For that, if you take a window of a old house, this is the bottom of the window and this is the top of the window. At bottom and top, the thickness is more for the oldest window. This is because the glass is being amorphous substance. It has a flow in this direction, just like liquids. So glass is a super cool liquid and it belongs to amorphous solids. You know why glass appears milky? This is because in daytime it melts, whereas in the night time it solidifies. Because of that reason, it appears like milky. And these amorphous solids are isotropic. Since they have irregular pattern of arrangements, this is a irregular pattern of arrangement. The physical properties such as conductivity and refractive index in this direction or in this direction would be the same, because the spheres are almost same in all the directions. That is why the physical properties will be the same in all directions. Such phenomena is called isotropic. And these amorphous solids, Best example for amorphous solids are plastic, glass, cellophane paper, and a starch is little bit amorphous and also crystalline. When we have look at slides for this amorphous and crystalline solids, and if you observe the differences between them, how they are related, how they are differs with each other, let us see in the next slide. If you look at this crystalline solids are symmetric, anisotropic. You know what crystalline solids are? Diamond, NaCl, and this is carbon in the form of graphite. Graphite is soft, it is a little bit of crystalline structure, but they comes under solid state, that is crystalline solid. Graphite is a crystalline solid. And if you observe the graph here, temperature versus time, if the crystals are cooled, they have no smooth cooling, that means gradually cools. And if the crystalline solids are heated at a particular temperature, the whole substance will melt. That is why they have sharp melting point. And this yellow picture is showing the anisotropic nature of a crystal. These rings are regular pattern of arrangements, and in this direction the pattern of arrangements of atoms are different. In this direction is also different. That is why this crystalline solid will have different properties in different lengths, that is known as anisotropic. If you look at the amorphous forms, amorphous means no form, rubber, glass, all these are examples for amorphous forms. Amorphous forms have no sharp melting point. They melts over a range of x to y temperatures, and this temperature versus time graph, while they are cooling, they undergo smooth cooling, and here this particular pattern is isotropic, because in amorphous solids the properties of the solid is same in any direction, that is known as isotropic. This particular thing shows the glass window is thick at the bottom and also at the top, because glass is a supercooled liquid, it having flowing tendency, it flows. Now let us take the differences between amorphous and crystalline solids. Diamond, gems, NaCl, these are symbols for crystalline solids. Plastic, rubber, glass for amorphous solids. Crystalline solids have regular three-dimensional pattern of arrangements, whereas amorphous forms have irregular arrangements. Another difference is, in crystalline form, long range order of patterns are present, whereas in amorphous form the repeating units are very short, so short range order. We know already the crystalline solids have sharp melting point, amorphous forms have no sharp melting point. Crystallines are anisotropic, amorphous forms are isotropic. Crystals are true solids, whereas amorphous are known as pseudo solids because they flows. crystalline solids are more stable than amorphous. When a crystalline solid is split into two pieces, newly generated surface is having plain and smooth cut, clear cut, whereas amorphous forms, when it is broken into pieces, they have irregular cuts, irregular cleavage takes place by amorphous solids. Let us move to the next topic, that is classification of crystalline solids. Based on the nature of forces exist among the constant particles, crystalline solids are classified into four types of solids: molecular solids, ionic solids, metallic solids, and covalent solids. If you look at the molecular solids, the constant particles are molecules. They are held by weak van der Waals forces. That is why these are very soft. Molecular solids again are of three types: non-polar molecular solids, polar molecular solids, and hydrogen bonding molecular solids. Non-polar molecular solids, for instance, if you take white phosphorus, sulfur, solid SO2, these are held by only London forces or weak forces. That is why they are non-polar molecular solids. Polar molecular solids are polar molecular solids are solid CO2, dry ice. Different CO2 molecules are held by dipolar attractions, and ice comes this hydrogen bonding molecular solids. So they are soft and they have low melting and boiling points when compared to the rest of the solids. When we talk about the ionic solids, the constant particles are ions, opposite charged ions. Since they have regular pattern of arrangements, they have high melting points and boiling points, but their melting points are generally lesser than covalent solids. Ionic solids are insulators in solid state, conductors in aqueous state. In ionic solids, they have different pattern of arrangements, and the further ionic solids are classified to NaCl type, ZnS type. All these are other type of classification. So, in these ionic solids, best examples are sodium chloride combines to give sodium chloride. magnesium oxide is an ionic solid. When we talk about the metallic solids, the constant particles are metal atoms. Constant particles are metal atoms. In the metallic solids, different metal cations are present like this, and the electrons are just like sea of electrons. If you connect to a wire, it conducts electricity. Metallic solids are good conductors of electricity because these free electrons are also responsible for the conductivity of electricity as well as temperature. Because of the free electrons, metals are luster, that means they have shiny surfaces. Because of the free electrons, the metals are malleable, that means the metal can be molded into thin sheets and wires. So, these are the properties of metallic solids. These are also having high melting points because of closed packed arrangements. When we talk about the covalent solids, these covalent solids are also known as network solids. The diamond, graphite, silica, quartz, tridymite, all they are comes under covalent solids. They have very high melting and boiling points. And these covalent solids are very hard in nature because of strong chemical bonds are present between atoms. So, constant particles are atoms in the covalent solids. So, if you have a look at the 4 types of solids, that next slide will give you better idea on this covalent solids. If you look at molecular solids, there are 3 types: non-polar, polar and hydrogen bonded. So, this HCl solid in state belongs to polar molecular solids, and this water belongs to hydrogen bonded molecular solids. And if you take this example, this is just like phosphorus, chlorine in solid states. They belongs to non-polar, argon, CCl4H2I2CO2. Generally in objective questions, they will give questions like this: which one of the following is a molecular solid? First option NaCl, second option copper, third option SiO2, and fourth option is argon. Then the molecular solid answer is argon. For that purpose, the study of these types of molecular solids are useful. Then come to the ionic solids. They have high density and melting points because of this close arrangement of opposite charged ions. You see metallic solids, copper, iron, silver, magnesium, the positive centers along with their ions, they are good conductors because of free electrons. Covalent or network solids, this is the structure of diamond. Carborundum, aluminum nitride, graphite, SiO2 are examples for covalent or network solids. Let us move to the next topic, that is crystal lattice and unit cell. So, this entire pattern of arrangement is crystal lattice. Crystal lattice means the 3-dimensional pattern of arrangement in which different spheres are arranged is known as crystal lattice. Say this whole thing is crystal lattice. Atoms are arranged 3-dimensionally here. If you consider a basic part in it, suppose basic part like this. This basic part is called unit cell. This whole thing is crystal lattice, and the basic part which repeats 3-dimensionally, x direction, y direction and z direction. 3-dimensionally to generate the crystal is called unit cell. In the crystal lattice, atoms are arranged in proper positions. Position of each atom in the crystal is called lattice point. Different lattice points gives rise to entire crystal. Let us have the unit cell. Unit cell is characterized like this. This is one unit cell. It appears like a cube, so it is a cubic unit cell. In this, this is one face of the crystal, next face, another face. Unit cell is composed of 6 parameters like alpha, beta, gamma, A comma, B comma, C. This is A, this is B and this is C. A, B, C denotes what? They are crystal phase lengths. This is phase length, phase length, phase length. And alpha, beta, gamma. The angle between B and C is alpha, A and C is beta, angle between A and B is gamma. In different unit cell, the alpha, beta, gamma angles may be equal, may not be equal. So, based on the 6 parameters, the unit cells are formed. So, different crystal systems we have is because of the arrangement of the 6 parameters. We have 7 crystal systems. 7 crystal systems. The 7 type of crystal systems is naturally formed is because the unit cell is having these 6 parameters. Let us have a look on the 7 types of crystal systems. Let us talk about simple cubic systems. See, this length and this length. This length, this length, this length. A, B, C. A is equal to B is equal to C. They are equal. This is alpha, beta, gamma. alpha is equal beta is equal gamma is equal to exactly 90 degrees. If the parameters are like this, it is called as simple cubic, and this length are equal, but this length is not equal. That means A equal to B, but B is not equal to C. This kind of crystal system, unit cell system, is called tetragonal. Here alpha is equal to beta is equal to gamma, but their angle is 90 degrees. When we talk about orthorhombic, this length A, this length B, this length C. See how they are? They are different. A is not equal to B, B is not equal to C in this case. But alpha is here, this is gamma, alpha, beta, these angles, interplanar angles. Alpha is equal, beta is equal gamma, they are also 90 degrees. So, in simple cubic, tetragonal, orthorhombic, the interplanar angles are same, that is equal to 90 degrees, whereas the face length is same in simple cubic, two faces are same in length, here three faces are in different lengths. In this way, altogether these 7 types of lattice arrangements are there. If you know, all these 7 type of crystal lattices gives 14 three-dimensional arrangements. All these 7 lattice systems gives 14 kinds of three-dimensional arrangements. Those 14 kinds of three-dimensional arrangements are said to have Bravais lattices. So, in the next slide, I would like to explain about triclinic, rhombohedral, hexagonal and monoclinic. Let us see. When we talk about monoclinic crystal system, here this length the length is different, whereas remaining 2 lengths are same. That means alpha is equal to beta, and the angle between the alpha is equal to beta is 90 degrees, and the lengths are 3 lengths are different. This length and this length ABC are different. Similarly, in a triclinic crystal system, here the 3 lengths are different and the 3 angles, interplanar angles, are also different. This is very important. Alpha is not equal to beta, beta is not equal to gamma, which is not equal to 90, A is not equal to B, B is not equal to C. So, triclinic crystal is having different phase lengths and different interplanar angles. When we talk about hexagonal, in hexagonal alpha is equal, beta is equal 90, but gamma is nearly equal to 120. In rhombohedral crystal, the ABC lengths are same, alpha, beta is equal to gamma, but these angles are not equal to 90. So, in this way we have 7 lattices systems, 7 lattice systems. This is the basic unit and these 6 are the parameters of the lattice. So, in the next topic, let us see the different kinds of unit cells. Unit cells are divided into 2 types based on the arrangement of lattice points or position of the lattice points. Primitive unit cell, centered unit cell. In primitive unit cell, that is P, the lattice points are present at the corners only. So, this space filling structure tells you this is the space filling structure, but actually these two spheres are not so far away, they are in contact with each other. Actual state is like this. One sphere is over here, another sphere is here. Look at this centered unit cell. Here the spheres are present at corners and also somewhere. So, centered unit cells are either body centered unit cell, if you look at this, in body centered unit cell, spheres are at corners and one sphere is at body centered. This is body centered unit cell. Face centered unit cell. Look at this. Spheres are at corners. See, this is a face at its center. At its center, 6 faces will have 6 centers. This is face centered unit cell. End centered unit cell. In the end centered unit cell, spheres are present at corners and also on opposite side faces. These two faces are opposite to each other. These two faces are opposite to each other. This is A face, this is B face, and this is a C face. So, body centered unit cell is also denoted with I, face centered unit cell is F, end centered unit cell is denoted with either A or B or C depending upon the opposite faces and their occupancy. So, basically these 4 kind of unit cells exist in all the crystal systems. When we talk about the sharing of the sphere at the lattice points, suppose a sphere present at corner is shared by 8 other unit cells. In which way? Suppose this is a sphere at corner, this is shared with 1, 2, 3 and its backside 4. Similarly, if we assume the 3-dimensional, in this direction, in this direction, in this direction, 3 more unit cells are added. and then from back direction fourth unit cell are added. Totally this cornered sphere is being shared by 8 unit cells. So, the contribution of this sphere per unit cell is 1 by 8. If you talk about the sphere present at the body center, only this body centered sphere belongs to this unit cell only. So, there is no sharing. So, contribution of spheres to this unit cell is 1. This is one contribution. If you talk about the sphere present at a face center, this is a face at its center. At this face, there will be another unit cell is being sharing this atom. So, this atom half belongs to this unit cell, remaining half belongs to the next adjacent unit cell. So, sphere present at the face center is shared by 2 adjacent unit cells. So, its contribution to the unit cell is only half. And suppose there is a crystal exists like this. For corners, how much sharing? How much fraction should be taken to this unit cell? 1 by 8. For face center, 1 by 2. At body center, 1. If you talk about this edge center, this is edge center. So, edge center sphere is shared by 4 unit cells, 1 unit cell and the remaining 3 are arranged later. So, this edge center unit sphere contribution is 1 by 4. That is how the contribution of spheres to their respective unit cell are taken while calculating the problems. Corners 1 by 8, face center 1 by 2, sphere at body center is 1 unit cell is shared by 4 unit cells. Body center no sharing. So, if one atom is present, contribution to the unit cell is 1. So, in this way the types of unit cells, basically these 4 types we explained till now. Now, in the nature there are so many crystals. In any crystal, sometimes all these 4 types of unit cells may be present. Sometimes only one type of unit cell may be present. So, all the crystal systems, we have 7 type of crystal systems. These 7 type of crystal systems will have 14 Bravais lattice. So, let us see what is Bravais lattice. There are 14 possible 3D lattices. This was observed by Auguste Bravais, who is a French mathematician. He is not a chemist. Mathematician, in the year 1850, he determined the various kinds of crystal structures and proposed in the form of Bravais lattices. So, if you take a cubic unit cell, with the cubic unit cell, primitive cubic, this is body centered cubic and face centered cubic. So, the cubic unit cell will have 3 Bravais lattices, whereas tetragonal, see tetragonal unit cell, tetragonal system is having two � lattices. One is primitive, second one is body centered. Body centered is represented with I. So, for tetragonal, P and I � lattices are present. The only one crystal lattice which is orthorhombic, it is having all the four kinds of � lattices. All the four kinds: primitive, body centered, face centered and end centered. If you look at the hexagonal system, only primitive, because in the hexagonal crystal system, the angles between A and B is 90, but gamma is not 90, it is 120. So, it is impossible to fit the crystals or spheres in the centers of the face or body centered. So, only one � lattice is present. Monoclinic crystal system is having two � lattices, primitive and this end centered. And last two types of crystals, triclinic and trigonal, they have only two, one each primitive unit cells. Altogether, if you count, for cubic 3, for tetragonal 2, 5, for orthorhombic 4, total 9, 10, 11, 12, 13, 14. These are the 14 � lattices practically proved by the �. Let us discuss how the objective questions will be given for the students who are eagerly waiting for their competitive examinations. Which of the following is anisotropic? My question is, which of the following is anisotropic? Option 1 is NaCl. Option 2 is cellophane paper. Option 3 is plastic. Option 4 is rubber. When we talk about the amorphous and crystalline solids, I already discussed that crystalline solids are anisotropic. So, among these four options, you have to find out which one is the crystalline solid. Obviously, NaCl is the crystalline solid, so that its properties are different in different planes, which is known as anisotropic. So, answer is NaCl. Let us have one more question, which is not amorphous solid. Cellophane paper, four is all. You know, plastic is amorphous, cellophane paper is also amorphous, whereas MgO is crystalline. This is crystalline. So, the question is, which is not amorphous? Not amorphous. So, crystalline is the answer. So, second option is correct. Let us take a third question. Whose melting point is lowest among the following. Melting point is lowest among the following. Diamond is network solid, high melting point. NaCl, ionic solid. SiC is also network solid, network or covalent. This is also network solid. This is ionic solid. This is molecular solid. The melting points order covalent having more melting point than ionic, than metallic, whereas molecular solids have lowest melting point. So, lowest melting point is solid SO2. Let us take one more example. Question is the unit cell parameters for tetragonal crystal system. Options are like this. In tetragonal crystal system, this is the tetragonal crystal system. This is A, this is B, this is C, facial lengths. These are interplanar angles. So, alpha, beta, gamma are 90. A is equal to B, but this length is not equal to C. That is why the answer is A is not equal to A is equal to B, B is not equal to C. See here, A, B are equal, C is not equal. Alpha, beta, gamma angles are 90. So, this is the tetragonal. What is the first option? It belongs to, we know that all the faces lengths and angles are different in triclinic. This is triclinic crystal system, whereas this is tetragonal crystal system. Let us take number of atoms per unit cell of BCC, body centered cubic structure. 2, second option 3, third option 4, and the fourth option is 5. Number of atoms present per unit cell of BCC. Let us have the BCC structure. In BCC, spheres are present at corners. You know what is the contribution of each sphere at corner? 1/8 part. And at body center, 1. So, how many corners? 1, 2, 3, 4, 5, 6, 7, 8. So, at corners, 8 into 1/8 is equal to 1. At a body center, 1 equal to 1. So, number of atoms per unit cell of BCC is 2. So, answer is 2. In this way, the questions will be given in the competitive examinations.